Hi class. In this video I'm going to talk about how we describe samples. And so what we're going to cover is charts and graphs, so basically visualization. So we'll talk about frequency charts or tables, histograms, and bar charts. And then additionally we're going to talk about measures of central tendency, and we use those typically to describe the average performance in a sample. So we'll talk about the mean, median, and mode, which are the three most commonly reported measures of central tendency, with the mean overwhelmingly being the most common. When we talk about frequencies, there are different types of frequencies, and three kind of broad categories are simple, cumulative, and relative. With a simple frequency, my saying is, if you can count, you can do simple frequencies. Literally, we are just trying to count the number of individuals that fit a certain score or fit within a certain group. So if we wanted to know how many guys we have in the class, how many women we have in the class, we could do a simple frequency and literally just men would raise their hands, I would count them, and boom, we would know the simple frequency for men. Underneath simple frequency, we have two types. We have grouped and we have ungrouped. With ungrouped, these are individuals where we focus on a particular score or a particular category. So if I wanted to know somebody's IQ exactly, how many people have an IQ of 90, those individuals would indicate that on a survey, or they would raise their hand, and then I could count the number of times that a score of 90 occurred. In a group, I can look at individuals who have an IQ from 80 to 89, for instance, and I can count all those individuals. I group them together so that they are all counted in that one larger overarching category. So, for example, if we were doing basically the same thing with test scores, I could ask you what your individual score is, like the 90, that would be ungrouped. Or I could ask you, did you get an A, B, or a C? Well, now what I've done by creating those larger groupings, those larger categories, is I'm creating a grouped frequency as opposed to an ungrouped frequency, where A would encompass the intervals from 90 to 100 typically, and then 80 to 89, as we see here. Once we have simple frequencies, we can do cumulative frequencies. And my saying for that, if you can add or sum, right? They're interchangeable. If you can add, you can do cumulative frequencies. So with cumulative frequencies, basically we're trying to say how many scores happen at a point or below it or above it, depending on our starting position. So if we start with the lowest possible score, let's say that we are talking about test scores, the lowest score is, I don't know, a 63. And so we start with that score and we say, how many people scored a 63 or below? Well, if only one person got a 63, the cumulative frequency at that point is still just one. Now, when we get to the next score, let's say that it's a 65, and there's one person that got a 65. The cumulative score for 65 is the one from that person plus the one from the person that was below them. So the cumulative score for 65 is actually 2. And I'll show you an example of that here in a moment. But basically, what we're trying to do is summarize the number of scores or the number of categories that are at a point or below it. We can also do the same thing starting from the highest possible score. How many people got, let's say the highest score was 100. How many people got a 100 or above? Well, nobody got above 100 because that was the maximum on the exam. 2 people got 100, that would be the cumulative score. The next highest score was a 98. One person got a 98. So we have 200s and a 98. Thus, my cumulative frequency would be 3 because it encompasses everybody at that score, 98, or above. And we'll show how to do that here in a moment. With relative frequencies, my little saying is if you can divide, you can do relative frequencies. Really, with a relative frequency, we're looking at the proportions of scores that occur at each interval or within each group relative to the total number of scores. So if one person got a 98 and 20 people took the test, the relative frequency for 98 would be 1 divided by 20. It's the proportion of people who receive that score in relation to, relative to, the entire number of people taking the test. So let's walk through an example, because a lot of the times in stats, it's easy to talk about it, and A lot of the times you'll get that quizzical look on your face, and in an online class, I can't see that, but it's common. It happens. And when we look at it concretely, you go, oh, it makes sense. Now, the problem is when you go to do the homework, you go, wait, what again? The great news in an online class, you can just come back to the video, you can look at your notes, and it'll start to click for you. So know that that experience of this makes sense. And then you go to do the in-class practice or a homework or a quiz, and you're like, wait, did it make sense? It did at the time. You just need a little bit of a refresher. You need to practice using it a little bit, and then it'll stick. So with the simple frequencies, again, if you can count, you can do simple frequencies. So if we were doing this in a classroom setting, I'd have you raise your hand if you are 5 feet tall or 60 inches tall. And let's say that one person raises their hand. Literally, all I have to do is go, okay, Sarah, in the first row, thank you for raising your hand, right? Put the 1 down. And then I say, if you're 5 feet 1 inches or 61 inches tall, please raise your hand. 2 people raise their hands. I count them. We do that for the whole class. And so I see that 4 people in the class were 5'2", 4 were 5'3", 6 were 5'4", and so on down that line. Literally, all I'm doing is people raise their hands, I count those, and I have the simple frequencies. For the cumulative frequencies, let's assume that we start at the lowest height. We could start at the tallest, but we're going to assume that we start with the shortest person. We move the shortest score over. So the simple frequency for the shortest person, if we're starting with the lowest possible score, is the same as the cumulative frequency because there's nobody below it. So the cumulative frequency, again, is everyone at that point or below it, or if we're starting from the highest point, everybody at that score or above it. So in this case, because we're starting at the shortest person, everybody at that height or shorter. Well, nobody is shorter. So it's still just 2. Now, when we get to the next box, we have to take the original 2 people that are shorter than 5'1", add the number of people who are 5'1", and that sum, that total, is going to give us the number of individuals, the cumulative number of individuals who are 5'1" or shorter, and which in this case is 4. And then we would do it for the next one. So we have 4 people that are 5'1" or shorter. How many people are 5'2" or shorter? Well, we encompass all the people that are 5'1", add to it the people that are 5'2", and we then end up with 8. So we take our number below that, and we would just do that for every cell beyond that point. The only cell that's different is our starting point. So if we start at the lowest, we just can move the score over for the lowest individual. Basically, what we're really doing is we're adding a 0. So if it helps you to have a consistent process, basically 0, which is the number of people below 5 foot or 60 inches, 0 plus 2 is 2, 2 plus 2 is 4, 4 plus 4 is 8, and I know you know basic math. Again, the math in this class is not the hard thing. People come in, they're kind of afraid of math, they have that math phobia. Honestly, we do addition, we do division, we do subtraction, multiplication, squares, square roots. You do need to know your order of operations, so if it's been a while since you did PEMDAS, or there's another abbreviation, I don't use it so I can't remember it, but if it's been a while since you used those, do refresh your memory on those, but we really only do basic math. So you would go through, do that basic addition, and you would realize that when I get to the bottom, what that tells me is 40 individuals are 5'9" or shorter. It also tells me, assuming that 5'9" is where this really stops. And typically, if we had a class, there would be a few guys that were taller than that, and maybe 1 or 2 women. But in this data, if this is really the end of the data, it tells us there's 40 individuals that are 5'9" or shorter. It also tells us that there are 40 total individuals. Well, now that's useful to us because when we get into relative frequency, it's how likely is a score or how likely is an outcome relative to the total number of people. Well, now we know the total number of scores, we know the total number of heights is 40, so we're going to use that information. And we often talk about that as a big N. So we use little n and big N for a couple of different things, and we'll see later when we do mean how we use them a little bit differently. But they're always relative to each other, such that little n is a smaller subset of the larger n. In this case, the big N represents the entire sample, the entire number of scores, the entire number of heights in the sample, and the little n represents the frequency of an individual group, or in this case, the individual height. So 2 is one of the little n's. 2 is the little n for 60. It also happens to be the little n for 66. And 4 is the little n for 67 as a height. And 40 is the big N for the whole sample. So it's going to be the case that when we do relative frequency, the the simple frequency for each height changes, but the 40 for the entire group stays the same for each calculation. So when we do relative frequency, what we're going to do is create a proportion. Little n divided by big N. So we move little n over. Little n is a 2 for the first group. We then divide that by big N. Again, that denominator is going to be the same. So if it's been a while since you thought about numerator is the top, denominator is the bottom. So our numerator is going to change with each of these calculations. We are then going to get an answer. That answer is called a quotient, again, if it's been a while. So because we're dividing, the answer to a division problem is a quotient. And so we're going to find that 2 divided by 40, our quotient is 0.05. That is the proportion of individuals in this hypothetical class who are 60 inches tall. So 0.05. We can do the same calculation, of course, for the next one, it's easy. Then we see that 10% or 0.1 proportionally are 6 foot or 5'2", and we do those calculations for each one. Now, once I have done all these divisions, and again, note, the numerator is changing. The numerator always matches up with the simple frequency from that row. The denominator stays the same throughout the entire sample because that's the number of people or the number of scores in the sample. When we add them together, if we haven't missed something or data is not missing, which in real data sometimes it is, but if we haven't missed something, it should be that when we add all these proportions together, we find that they equal 1. If they don't equal 1, either data is missing, which in this class is rare, and I don't think I ever do it, or more likely, we made a little error. And in fact, in doing these calculations, I made an error. I hit a key wrong, and I ended up putting in 0.15. So when I did the calculation, I realized, wait, that doesn't equal to 1. I quickly looked back, and I realized, oh, I hit a 1 instead of a 0. No big deal. But if I hadn't checked, I myself would have gotten an answer wrong, because I'm human. It happens. So by having these little checks, by knowing what it should add up to in an ideal circumstance, you can then make sure that if you're making a small error, you catch it so it doesn't impact later calculations. Because once we calculate this relative frequency, here in a moment, I'm going to show you how to build on these 3 basic, simple, cumulative relative frequencies to do later calculations. If you go to build on this relative frequency and you calculated the first one wrong, every answer after that is wrong. That's also one of the benefits for the strategy in the homework, where if you work on it and then you talk with a peer about it, and then you come see me for clarification, hopefully through that process, if you made a small calculation issue, it comes to light. So one of the things that we do over and above to kind of build on this is to shift relative frequencies into percentages, or relative frequency percentages is the way you'll see it talked about in a lot of books, or relative frequency percent. So if we want to take a proportion, shift it to a percent, all we have to do is multiply by 100. So 0.05 times 100 gives us 5. We've done that for the first 2 groups. For the next one, right, 0.1 times 100 gives us 10. 0.15 when we get to 5'4", 0.15 is going to give us 15. When we get to, for instance, 5'8", 68 inches, 0.15 is going to give us 15 again. And with these, now I've shifted proportions to percentages. I've multiplied everything by 100. Thus, that outcome that I should have when I added the relative frequencies gets multiplied by 100. So before it was supposed to be 1. Now, assuming I don't have missing data, assuming I haven't made an error, it should be that if I take these percentages, I add them together, I get 100%. Thus, everyone is accounted for, and it would probably be likely that my scores are correct. It doesn't guarantee it. It's always possible that you make 2 errors that kind of offset each other. It's rare, and it doesn't likely happen. But if it's not 100, you definitely made a mistake or data is missing, which again in this class shouldn't happen. The last thing we're going to talk about as far as frequencies goes is percentiles. And you're probably familiar with these. We talk about them in stats often as cumulative frequency percent, but more commonly, you're probably seeing them as percentiles. When you took the SAT, you probably found out what percentile you were. When you took the STAR test or the TAKS test, you probably found out what percentile you were in. If you take the GRE, you'll find out what percentile you're in. What the percentile represents is basically a cumulative frequency at that score or below it. So when we look at this, for the first score, in this case, the first height of 60 inches, 5% of individuals are at that score or below. Again, because nobody is below it, it equals to the related percent. Because basically we're just adding 0 because nobody's below it. For the next step though, we're going to do what we did before, where we take the individuals below that, at this point 5, we add the next group or the next score to it, or the percent of individuals in that next group, and we see that 5 plus 5 equals 10. And then for the next one, 10 plus 10 equals 20, 20 plus 10 equals 30, 30 plus 15 from 64 inches is 45, 45 plus 15 from 65 inches is 60. And we see that when we get to the last percentile, assuming data is not missing, should equal up to 100. Now, in more complicated data, another thing that can impact this outcome not being exactly 100 is if you're having a little bit of rounding issues. So I note this in the homework assignments, but I'm just going to say it in this video as well. Make sure that you're doing all your calculations to 4 decimal places, and then when you go to report your answers, round to 2 decimal places. So look at your third decimal place. If it's 5 or over, round up. If it's below 5, keep it the same. And what that should do is make it so that when you add these together, if you're not rounding too much early on, you'll be less likely to have little rounding issues. So if, for instance, instead of being a nice, clean, easy 5% like the example provides, if it was something like 5.05, and I go, well, that's really just 5, and I round, if I do that too many times, I get down to the bottom, instead of equaling 100, it equals something like 99.2. Because of the rounding across those scores, when I sum, I'm missing part of my data. All right, so we know how to do frequency tables. Another way that we can present data is through visualizations, and 2 common visualizations are histograms and bar charts. And histograms and bar charts are used with different types of data. And we're going to talk more about types of data in a different video. But just as an introduction, 2 broad types of data are continuous data and categorical data. With continuous data, I can be any possible score. So whenever I tell you I'm 5'10", maybe I'm really 5'9" and 8/10, or maybe I'm 5'10" and 2/10, right? But we often end up rounding. But the unit of measure could be more precise, could be more exact. There is a continuum between 5'10" and 5'11", whereon if we wanted to be more specific, if we wanted to use smaller units of measure, we in fact could. Now, there is also data called categorical data. With categorical data, if you ask me what color eyes do I have, probably I'm going to tell you that they're blue, right? But is it just blue? Like, I could make it more nuanced, but at the same time, people will tell you basically, brown, green, blue, those are kind of the common ones. And so there is a distinction between each group. So histograms are used for presenting continuous data. Bar charts are used for presenting more categorical data. So when we look at this chart, we see that height, because it's continuous, each of these bars basically on the chart that represent the number of individuals who are 60 inches tall, 61 inches tall, they press against each other to kind of represent that 60 inches is right next to 61 inches and that there is a continuum beneath these. With bar charts, we have some space between each of these bars. So in this case, we see that we have two individuals, right, looking at that y-axis. We have a frequency of 2 for blue. We have a frequency of 4 for brown. We have a frequency of, it seems, 3 for green. So there are two individuals who reported that they had blue eye color. But importantly, and I know it seems small, but again, it fits with the way that we present categorical data where we have these nice categories. And of course, discrete data typically gets reported as a continuum as well, so it gets reported with the histogram. You can make these fancier. I'm not going to do that in this class. That's not really what we focus on. We're really trying to do an applied introduction. However, do know that if you wanted to build on your skills from this class, we often do workshops. Jason Roden often helps me. We do them in R and other programs where you can make visuals that are more appealing, more useful. And in fact, this eye chart could also be made in Excel fairly easily. And so you can create a bar chart, tweak the colors, and then it provides a more easy visual presentation. In addition to describing the frequency, showing these visualizations, we can also describe samples using measures of central tendency. Again, measures of central tendency are the way that we say, on average, within this group, what is going on? What is their general IQ score? What is their general grade? And three commonly reported measures of central tendency are the mean, which often in colloquially we talk about that as an average, the median, which is the middle score, and then the mode, which is the most common score or possibly scores if two scores occur with the same frequency. So starting with the mean, we can have a sample mean or we can have a population mean. The sample mean, depending on if you're reading in a textbook, like a stats textbook, or if you're reading in a journal article, will be represented as X bar in the stats book, or a big capitalized italic M in an article. The M is easier to typeset. It's a little less expensive for journals to pay somebody to typeset it. So because of that, they tend to use that abbreviation. In stats books, historically, we used X bar, and so they tend to use that abbreviation. So with the sample mean, to calculate it, all we have to do is sum the total number of the scores and then divide by the number of scores. So for the heights, if we wanted to do it, we would write out, okay, there was, I think, two 60s, right? So 60 plus 60, then there were two 61s, plus 61, plus 61. We would sum all those heights. So not just the possible heights, let's go back. So not just 60 plus 61 plus 62, we also have to account for the number of frequencies. So 60 plus 60, because it happens twice, plus 61 plus 61 because it also happens twice, plus 62 plus 62 plus 62 plus 62. You could also use multiplication, but you get the idea. We're summing together all of the heights for all the individuals, not just all the possible heights. And then we're going to divide by the number of scores, which in our data was 40. So here we see sigma, that's the letter that you see here that looks almost like an E. It's actually the Greek letter sigma, it's a capital sigma. What that means in statistics is add up or sum together all of the X scores. In this case, X represents the heights. Sometimes you'll see this X with a little I. The I is used as a counter or an indicator. So X1, the first person's height is 60. X2, the second person's height is also 60 if we have them in order. X3 would be 61, X4 would be 61, X5 would be 62. So sometimes you'll see that with little I, and then the number goes in and substitutes for that I if you're actually tracking which X you're talking about. So we would sum all those together, we would add all those together, and then we would divide by 40. We would divide by the total number. Now, the reason that we use little n here as opposed to big N is because when we're talking about sample means versus population means, the sample is a smaller subset of the population. So before when we were talking about frequencies, we were talking about possible scores, possible heights in relation to the overall sample. So in that case, the smaller group was a possible height of, say, 60 inches or 61 inches. So the n, the little n for each of those groups was 2 or 4 or 6 or whatever it was, and the big N for the overall sample was 40. But when we're talking about means versus populations, the sample is now the smaller, it's the subset of the population. Thus, little n is used to represent the total number of individuals in the sample, and big N is used to represent the total number of individuals in the group. So as I mentioned, we have sigma. It just means to sum or add together all of the x scores, all of the heights. And again, x is just standing in, like in algebra, it's standing in to represent a variable, whatever that variable might be. Height, IQ score, anything that you would put into it. In the population mean, we do the same basic process. The mean of the population is represented by the Greek letter mu. So this is the lowercase mu. It basically looks like a U with a tail. And we're going to do the same basic process. We're going to sum together all the scores, maybe all the heights of all the people in the population. So in the United States, there's give or take 350, 360 million people. You would add together all those people and then divide by the 350 million, 360 million. Of course, we're not going to do that. But if we wanted to do that, if we had the data to do that, we would just sum together the heights, right? Start with maybe the shortest person, go all the way to the tallest person, and then we would divide by, in this case, big N, representing that we have the total number of people in the larger population. So again, I know it's slightly confusing that we use little n and big N differently. I didn't choose that. It's the way it's done in the field. So just remember, depending on the context, little n and big N kind of change. Sometimes big N is used to represent the total number of people in the sample. Sometimes it's used to represent the total number of people in the population. But relative to each other, they are consistent. Little n will always be smaller. It'll be a subset of the larger n. In addition to the mean, we can also do the median. The median is the value at the median position, or the value at the middle position when the data are ordered. That is important. A lot of the times I give you data that aren't necessarily ordered smallest to largest or lowest to highest. You need to order them first before you decide what your median is, because you may very well realize what the median position is in the data, but if the data aren't ordered, whatever value is at that position is not actually the median until you rank them, until you order them. The median position is going to be n plus 1 divided by 2. So in a sample, we would take let's say there was 40, we would say 40 plus 1 divided by 2, and that's going to give me 41 divided by 2 is 20.5. Well, that's actually between two numbers. So when we have an even number of scores, what we would actually do is take the score directly above and directly below the median position, add them together, divide by 2. Basically, we're getting the average of those two scores. So if it was 20.5, the 20th score and the 21st score would be the two scores that we're interested in. So when we put the heights in order, the height of the 20th tallest person and the 21st tallest person would be the ones of interest. We'd add those two heights together, divide by 2. If it's an odd number of scores, it's actually easier, because the median, if there were, say, 39 people instead of 40, 39 plus 1 is 40, 40 divided by 2 is 20. So whoever is the 20th tallest person, when we put them in order, that is the median height. Now keep in mind, median position is the 20th. Median height is the height of the person who is at that position. So their height, maybe their height is, I don't know, 64 inches. That is the median. The median position is 20. It's the number that they are at when we set them in order. The last thing that we can do is look at the mode. And so the mode is the value or values that occur most frequently. So if we're looking at our original data, we see that this height of 64 and 65, both of them have a frequency of 6, as well as 68 inches has a frequency of 6. So individuals that are 5'4", 5'5", 5'8", in our data occurred the most frequently. And so looking at this, we now see that the mean, median, and mode may be different from each other. There's a single value for the median, there's a single value for the mean, there can be multiple values for the mode. Each of them, though, is trying to tell us about the average height in this sample. And so, because of that, each of them can be more or less valuable depending on the nature of the data. So, for instance, the mean is actually more susceptible to problems whenever there's an outlier in your data. So, if there was a really, really tall person, let's say that somebody who was 6'8" was in the data too. Well, you have heights of 60 to 69 inches, and then you have this person that's 6'8", and so they're going to be, what's that, like 80 inches, I think. So that person, right, who's about 80 inches tall, they're going to skew this data, they're going to skew it. Well, if I calculate a mean from that, is that really representing the general height in my data? I don't know that it is anymore. So we have to be aware of that. We have to look for those types of things. And your book talks about that more.